This is going to be the lecture over section 22.2, resistance and reactance. So if we have current that is given by this particular phasor equation, and the voltage between the 2 points is described as this. In other words, same type of algebraic relationship, except we're adding in something new here, a phi. This is going to be called the phase angle of the voltage relative to the current. In other words, these two may not necessarily be in phase with each other. So how do we represent that, or how do we change that? We throw this little term in here to try to help compensate for the fact that it's going to be a little bit out of phase. So the voltage across a resistor is in phase with the current, and the voltage and current amplitudes are related by this. The voltage across an inductor leads the current with a phase angle of 90 degrees. The voltage and current amplitudes are going to be related by this. So what we're seeing with a resistor is in phase with the current, and inductor leads the current with a phase angle of 90 degrees. This is why this is going in here. May not necessarily need it here for the resistor. The inductor is a different story. Now, the factor here that we see here, X of L is equal to omega times L. This is going to be called the inductive reactance of the inductor. The voltage across the capacitor lags the current with the phase angle of minus 90. Again, that's why that's added in there. The voltage and current amplitudes are related with this particular equation, where this is equal to this. Here, the inductance is related to X of L when it's multiplied by the angular velocity. Here, when we take X sub C, it is related to, it's inversely related to the capacitance with the angular velocity here in the denominator along with the capacitance. So here we have the inductive reactance, and here we have the capacitive reactance. So we can see here with the angular frequency moving on in this direction, we can see here that the resistance does not change very much here. However, when we're looking at the inductive reactance, we're looking at a straight line here, whereas the capacitance is more of an exponential relationship. So let's go to the section itself. All right. So what we're going to do is we're going to derive voltage current relationships for three of the most widely used and important circuit elements. You've got the resistor, you've got the capacitor, and you've got the inductor. You can think of these relationships as a generalization of Ohm's law for a resistor. So first, let's consider a resistor with resistance R, sinusoidal current, and we're going to represent that here. The current amplitude is capital I, and we're going to denote the instantaneous potential of point A with respect to point B down here with V sub R. In other words, potential difference is V sub R. For Ohm's law, this is given, of course, by the instantaneous current multiplied by the resistance. And then we know what the instantaneous current is, so we throw this in to substitute for that. So this is what we come up with. For plotting all of this, we have here that V sub R, of course, at any instant is going to be given by this particular equation. So we can see how it varies sinusoidally. We see how the current is going to be, how its amplitude and the voltage amplitude are given here. Again, this is related here with V is equal to I times R. With the amplitude of the current. Here we can see where, since these two are in phase with each other, they peak and they trough at the same time. You can see the phasor, and seeing as how V sub r and I, since they are pretty much in phase with each other, that these changes here in the instantaneous values are going to shorten and point in different directions pretty much at the same time. The only difference here being the magnitude. The maximum voltage is the coefficient of the cosine function. So you can also write here that this is going to be, the instantaneous value is going to be pretty much wherever this is pointing at during the rotation around the circle. When does this start to change? When would they be out of phase? Well, I'm glad you asked that. So that comes in handy here with an inductor in the AC circuit. So let's replace the resistor with a pure inductor with a self-inductance of L and a zero resistance. We're going to assume that the current description here remains the same. We know an induced EMF in the direction of I is going to be given in 2622, figure 26.26. We know that the EMF is going to be given as minus L times the change in I over the change in T. And of course, that's going to correspond to the potential here. So the potential is going to be the negative of E. So we're going to end up replacing the voltage here of this particular inductant circuit is going to be given with this. Now, this is going to be out of phase by 90 degrees. Again, we were going to add in 90 degrees because that's what we've observed for these types of circuits. This is what happens. So we know the voltage here, rather than starting at this particular spot, the voltage is going to start here and then going like this. Current, on the other hand, is going to start out here since it's 90 degrees out of phase. It starts at whatever, we're just going to have it start at the maximum value. And since this is 90 degrees out of phase, we're basically going to take this particular graph that we saw up here, and we're going to shift it out here 90 degrees so that it starts at 0. And this is the effect that we see. So since it leads by a quarter cycle, again, this is what we've got going on here. Since the change here for the voltage phasor and the phase angle is 90 degrees, we can see here for this particular angle that the voltage is going to end up at this particular angle plus 90 degrees. So the phasor here is now going to be what we see as far as the voltage within the inductor, as opposed to where the current phasor happens to exist. The mathematics here, as we go through and we want to describe the resistance at this particular spot, what we're going to do is, as we had with VR, which let's see, is up here, we're going to basically, for the VL, is we're going to substitute in VL for that. And let me see if I can find where VL is written. There we go. We know that this is what's going on with VL. So the change, or basically, how does this change with time if we, and obviously this course is not set up to talk about calculus, but if you were to apply calculus in this particular case, what you would do is you would be taking the derivative of this with respect to t, and that change with time ends up becoming this function. Now, it's not something I would expect you to see immediately, but that is ultimately what is going on here. We can then change this back to cosine if we use this particular identity. That is a trig identity. You may or may not have worked with that before, but that trig identity allows us to take this and change it into this. Since this is how we are describing current, and this is how we are describing voltage, both of these instantaneously, we can end up taking the voltage here and describe it using this particular value as the peak value. In other words, this part of it here disappears. We're just interested in what the maximum value is. That's where that comes from. Now, the inductive reactance is going to be this particular product. This looks very much like V is equal to IR, in other words, Ohm's law, but since we're dealing with inductors, it's not the exact same thing. So we're going to call this the inductive reactance, and it's going to be that particular product. So you can think of this as being substituted in for R if it were a resistance-only circuit. The unit is going to be the exact same as it is for resistance. It's going to be the ohm. Now, the capacitor in an AC circuit, we're going to again be taking the same description here of current instantaneously. And here you may think that the charge can't really move through the capacitor because its two plates are insulated from each other. But at each instant, as the capacitor charges and discharges, we have an amount of current into one plate and an equal current out of the other plate, just as though charge were being conducted through the capacitor. So for this, we also often speak about alternating current through a capacitor. Again, we're dealing with phases in this particular instance, and this is going to end up lagging. Because it lags, we're going to end up seeing a shift. The shift very much like what we had before. Voltage is going to be lagging by 90 degrees. So rather than have 90 degrees over this way, we're going to have 90 degrees this way for the voltage phasor. If we're looking for the voltage of point A with respect to B, if we look at the change of voltage with respect to time, this is what we end up with. It's 1 over C times the change in Q over the change in T, which this is described as current. If we take I as described this way and put it in here, this is what we end up with. Again, remember that the voltage in a capacitor is the same as Q divided by C, which is where this is coming from. So if we're looking at the change in time, or how this changes with time, the capacitance doesn't change, but the charge can. And so that's where a lot of these terms are coming from. Again, using calculus, if we go through and we want to determine, again, how this changes with time, this is what it comes up with. Since it is out of phase by 90 degrees, we have to factor that into this particular relationship. And so we are changing the sign here. Since we don't like to deal with that, we'd rather deal with cosine. We end up using a trig identity in order to be able to put that in. And when we do that, this is the relationship that we come up with. Again, maximum voltage basically chops off that trig term. And again, we are looking at something that's comparable to V is equal to IR. And we end up with something called the capacitive reactance. And that's where this comes from. So the voltage of the capacitor at maximum is equal to this relationship. So you have some other problems here that you can go through. I would encourage you to do that. Now, if we are looking at current or circuit elements with alternating current, we have what those elements are here. We have the circuit quantity, basically, what does resistance look like with each one of these? The amplitude relationship, how does the voltage vary with these attempts to model the resistance? And how does the voltage react as far as the phase with the current? And this is a table that describes all of that. If you were to plot it, this is what it would end up looking like. You can see here in this particular amplifier, the inductor and the capacitor feed low frequencies mainly to the woofer and high frequencies mainly to the tweeter. So this is how these particular, you've got resistors here, but as far as the tweeter is concerned, you've got a capacitor here. As far as the woofer is concerned, you've got an inductor here. So those are some elements of each types of circuits that you need to bear in mind.